Welcome to the Explainer. Today, we're tearing down one of the most common, and frankly most dangerous, assumptions in web development. If you write JavaScript, you've probably used the classic JSON parse, JSON stringify trick to quickly clone an object. It's literally everywhere, and it feels completely safe, right? Well, I hate to break it to you, but if you're treating JSON as a perfect, lossless snapshot of your JavaScript state, your JSON is lying to you. Today, we're going to look closely at why JSON completely erases JavaScript types and why this widely trusted technique is secretly altering your data. Imagine you're working with a massive number. It's a huge identifier, maybe a critical database ID or a customer invoice number. This specific one happens to end in a 3. But here's the kicker. If you were to drop this exact number into a JavaScript object and run json.stringify on it, the resulting JSON string would actually end in a 2. It silently, effortlessly mutates into an entirely different number. So how does this silent mutation happen right in plain sight? And honestly, more importantly, why doesn't the runtime throw a single error to warn you that your database ID just got corrupted? No red flags, no warnings. Your application will just keep running, blissfully aware that it's now passing around the completely wrong data. Okay, let's dive into our roadmap for investigating this today. 1. The great JSON lie. 2. How JSON erases types. 3. Hidden serialization traps. And 4. Building safe JSON boundaries.
Starting off with Section 1, the great JSON lie, or as I like to call it, the illusion of the clone.
When you serialize a varied object, say one that contains undefined properties, a date object or a NaN calculation, the copy you get back loses its original shape completely. That date object, it instantly degrades into a plain string. That NaN value, it transforms into null. And any property you had set to undefined simply vanishes into thin air as if it never existed. The object passes through the most familiar serialization round trip in JavaScript, yet the copy you get out no longer carries the same data or types as the original you put in. Which brings us to Section 2, how JSON erases types, which is really a story about the minimalist design of a wire format. You see, there is a fundamental disconnect here. On one side, we have JavaScript's rich, evolving type system. We're talking dates, sets, maps, regular expressions, and bigins. On the other side, we have JSON's incredibly sparse vocabulary. It only supports strings, numbers, booleans, null, arrays, and objects. JSON simply doesn't have the grammar to express most of JavaScript's advanced types. It's kind of like trying to translate a complex novel into a language with only 50 words. So when data crosses the boundary, it gets forcefully squeezed into these limited JSON primitives. To understand why it's built this way, we have to look back at history. JSON emerged around 2001 as a lightweight alternative to XML for exchanging structured data between browsers and servers. It was formalized in 2006, with the current standard published in 2017. The absolutely crucial point to remember here is that JSON was built as a minimal, language-agnostic interchange format. It was meant to be easily readable by Python, Go, Java, and Ruby. It was never intended to be a one-to-one JavaScript memory dump. Its minimalism is its superpower, but it's also exactly why it strips away your JS-specific types.
This really highlights the visceral before and after of that type erasure. Think about a date. It produces an ISO string when serialized, but when parsed back, it just stays a string. The runtime has no idea it used to be a date. Or look at a set or a map. They store their state internally, so JSON just outputs completely empty objects. But the most dangerous one for sure is NaN becoming null. Because of this, downstream code can literally no longer distinguish a mathematical calculation error from a measurement that was simply unavailable. The entire meaning of the data has been silently altered.
Let's move into Section 3, hidden serialization traps, specifically code execution and silent mutations. You really have to start treating json.stringify as executable behavior, not just a passive snapshot. It actively triggers hooks in your code. For instance, if an object has a custom toJSON method, stringify is going to automatically execute it and serialize the returned value instead. If you have an enumerable property backed by a getter, reading that property during serialization invokes the getter. And guess what? If your getter throws an error, your serialization crashes. Also, we have to talk about how wildly inconsistent undefined is handled. It's entirely omitted from objects, but in classic JavaScript fashion, just to preserve the order in arrays, it gets converted to null. Now let's finally solve that mystery from the very beginning of the explainer. Why did our huge database ID change from ending in a 3 to a 2? Well, the shocking truth is that the precision loss happens in JavaScript before JSON even sees the number.
JavaScript stores ordinary numbers using the IEEE 754 binary 64 format, which only has 53 bits available for the exact integer. Because our ID exceeded that limit, JavaScript quietly rounded it while evaluating the number literal itself, long before JSON.stringify was ever called. The damage was already done.
And that brings us to another massive trap: how these two systems handle references. JavaScript happily maintains complex graphs and circular references, where an object points back to itself or maybe its parent. But JSON hits a hard brick wall here. JSON records values, not references. If the serializer detects a cycle, it immediately throws a type error right in your face. This often surfaces far away from where the object was actually created, typically crashing your app during a routine log or when returning an HTTP response.
And the traps definitely don't stop there. Have you ever relied on the order of keys in a JSON object? Don't. While modern JS specs guarantee property order, the JSON spec officially defines objects as unordered. So if you send that JSON to a Go service, the map iteration order is completely unspecified. Also, you have to be incredibly careful about parsing untrusted input. Malicious keys like __proto can lead to prototype pollution if you recursively merge them without checks, and extreme nesting can cause immediate resource exhaustion and just crash your server altogether.
All right, let's get into solutions. Section 4, building safe JSON boundaries and how we can stop treating JSON as a lossless snapshot.
This basically leaves us with 3 practical rules for creating strict data contracts. Step 1, we must explicitly define the wire shape. Step 2, we have to tag exceptional values so they survive the trip. And step 3, we must ruthlessly validate the data immediately after parsing it.
Let's apply Rule 1 to our large integer problem. To prevent precision loss, you absolutely must explicitly define string shapes for large identifiers. By turning that massive ID into a decimal string before serialization, the JSON implementation preserves the digits exactly. Then the consumer on the other side can parse it as a string and safely convert it into a big int if they actually need to do arithmetic on it.
For Rule 2, we solve the type erasure problem by implementing a shared protocol. If you need a date to truly remain a date across boundaries, you can't let it silently degrade into a standard string. Explicitly tag it. By structuring it as an object with a $sign property set to date and a value property containing the string, you give the receiver all the context they need. A reviver function on the receiving end can then spot that tag and safely, accurately reconstruct the original date object.
Finally, Rule 3, validation. JSON.parse only checks for syntax. It doesn't care at all if the data makes logical sense for your app. You must use runtime schema libraries like Zod or Typebox immediately after parsing. This creates a solid wall rejecting invalid shapes, unexpected types, or malicious prototype keys before your core business logic ever decides to trust the data. It all boils down to this: JSON is not broken. The mistake is treating it as a lossless snapshot of JavaScript state. It's an incredibly useful tool because its data model is small, it's lightweight, and it's widely understood. But a JavaScript object and its JSON representation are 2 totally different data models, and bridging them requires explicit, careful conversions. So this leaves us with a critical question to ask ourselves about the systems we build and maintain every day. Are your application's types quietly disappearing across the wire right now? Take a close look at your data boundaries, check on those large integers, and make absolutely sure your JSON isn't lying to you. Thanks so much for joining me for this explainer. Now go check your APIs and keep learning.